in this very classical setting. So I'm focus of my talk will be minimal and constant mean curvature surfaces in R3 and 3 manifolds. Okay, some results generalize to other dimensions or even other codimensions. Most other things about codimension 1. I was surprised. There's actually some of the proof techniques, which I'm not going to talk too much about, actually are closely related to some things in Simon Donaldson's talk. These pointed Hausdorff, Gromov-Hausdorff limits of spaces. In my case, this is spaces, manifolds with boundary and maybe with additional structures such as foliations with other structures. Anyway, so maybe it's just curious. Why are there so many really fascinating, more interesting results in dimension 3? And it's really, again, this talk is a little bit related to the first talk about singularities, formation of singularities, properties of singularities, limit tangent cones of singularities, uniqueness of limit tangent cones, things like that. So why dimension 3? What's so special in dimension 3? Why is that somehow giving us really deeper results than we see, in my opinion, see in higher dimensions? And that's because it's really the only dimension where you have a conjecture which isn't solved, which we strongly believe. You cannot have a sort of a minimal varifold or a constant mean curvature varifold with an isolated singularity. This is a codimension 1 kind of question. So we're looking at codimension 1. Can you have somehow an embedded sort of minimal or constant mean curvature object with an isolated interior singularity? Okay? It's not even true in the plane. You can have two lines cross. So there's a good example. It's not true in the plane. It's certainly not true in like dimensions higher than 3, because you could take a minimal hypersurface in a sphere and just take the cone on it, right? The cone, that's a minimal variety. So something's very special in dimension 3. We don't know this conjecture, but it's certainly true. It's certainly one of the main goals of the subject is to resolve this question. Can you have an isolated interior singularity? Okay, so let me start at the beginning with definitions. This just makes everything easier and faster in the talk, right? We have all these shorthands. Okay, if you see green, that's probably a number bigger than or equal to 0, and it represents the constant mean curvature of a surface. So if you see blue, it's not going to be the mean curvature. It's some other number like genus or dimension or something like that. So we have M is a H surface, means that it has constant mean curvature, that green H, okay? It could be a 1 there. It could be a 1 surface. If it's in green, we're talking about constant mean curvature. Okay, standard definition that we have from variational property of these surfaces is that constant mean curvature represents critical points to compactly supported variations, critical points of area, with respect to volume-preserving variations. And we have our classical examples, and I'm going to be talking more about why these classical examples are so special in this setting. Okay, so we have the sphere, the cylinder, and Delaunay surfaces. Okay, and of course, specializing to the case H equal to 0, we have our minimal surfaces, and again, kind of a special theory in that case. And we have, again, two very important examples, plane and, we have the plane, of course, we have the catenoid, and we have the helicoid. Again, I'll be making some remarks about why these surfaces are so special to the whole theory. Actually, very theoretically important examples. They give rise to techniques of proof. Okay, so we have our sort of visual picture of minimal surfaces as soap films on wires. And soap bubbles are these constant mean curvatures, say positive surfaces. It's like you have a soap film and you just have a constant difference air pressure on each side. So we have that sort of these physical intuition we gain from these sort of ideas. In particular, when you solve an isoperimetric problem in a 3-manifold, say a compact 3-manifold, fix a volume, try to minimize the perimeter of such a volume, we get constant mean curvature surfaces because they satisfy this sort of variational property. Okay, so here's the question. This is a hard question. You might think it's an easy question. This is a question which I've wondered about for many, many years, like 30 years. So the question is, you look at the round sphere in R3. Okay, so it's a surface which has non-zero constant mean curvature, right? So I'm looking in general for a complete simply connected. So that means, well, a sphere, I think I understand the problem. They're all the round spheres. But can I put a plane? Can I put a plane in R3 with constant mean curvature? It's not minimal. I mean, of course, I can put a flat plane. I can put a helicoid. But can I put a plane with non-zero constant mean curvature in R3? It's a surprisingly difficult problem. So this is a problem that goes back about 30 years ago. I was really thinking about this kind of question. Okay, so we certainly need, if we're going to answer that question, we certainly have to eliminate the cylinder, but it's not simply connected, right? And you can take the complex plane. There are lots of proper immersions of the constant mean curvature. So we can, if we're willing to let self-intersections, it's not, there are lots of self-intersecting surfaces. So it's a really question of being simply connected and embedded. So embedded plays an important role in a lot of these theorems. They're just not true if you don't say embedded. And the answer is yes. Simply connected, complete, intrinsically complete surface in R3 is, in fact, a round sphere. So how do we get to this? Okay, this is true. There are probably lots of reasons why it's true. We're going to at least see some of the reasons why it's true. There are lots of different approaches, and you can say, oh, yeah, that's a reason why it's true. That's a reason why it's true. And then this gives us more insight and even to local questions. This kind of question actually gives rise to insight, heuristic arguments that maybe can be made rigorous. Okay, so a little history on the problem. So yes, round spheres are the only complete, simply connected surfaces embedded in R3 with non-zero, very important, non-zero constant mean curvature. So like I said, I've been interested in this problem a long time. I guess this result really goes back to about 1986. It was published in 1988. But I could figure this problem out if I assume an additional key property that the plane that I'm interested in was properly embedded in R3. So I could try to say I have a properly embedded plane in R3. That's important because when I intersect with a big ball, I get a compact surface, and I can do more things with compact surfaces, right? I mean, right now, beforehand, maybe you could put a plane of constant mean curvature, embed it in a ball, right? It definitely would not be proper. Maybe it's instead of a ball. Okay, so so in the case of minimal, we have these sort of recent, very beautiful results that characterize planes that are minimal, complete, and embedded in R3. So you have the plane, you have the helicoid, and you have the round sphere. Okay, again, knowing this is actually very, very useful for understanding the previous problem by scaling. You can imagine scaling. Constant mean curvature surfaces produce minimal surfaces. Maybe they're also simply connected, and then we can get some insight into the problem. Okay, so everything on this slide, I kind of run out of space. This is like, if you don't know the subject, I'm going to tell you all the key historical results, okay? So everywhere on this slide, the surfaces I'm talking about are embedded. I just didn't have space to put the word embedded, but every surface I'm talking about here is embedded. So going back a long time ago, you don't have any one-ended, remember the blue means like one, this means something else other than mean curvature. One surface, that means constant mean curvature 1. Surfaces of finite genus in R3, okay? That's right. One-ended finite genus means simply connected, so or topologically plane. So that goes back to the proper problem, and sort of extending and going a little beyond what I was working on there. One can in fact characterize the asymptotic behavior of constant mean curvature surfaces of finite topology. Okay, so for example, take an annulus in R3, properly embedded, constant mean curvature, non-zero. Then in fact, you are actually a surface revolution. You're what is called an unduloid or a Delaunay surface. Okay, so we have those surfaces, all right? And these become the canonical representatives for which you're asymptotic to. So if you take any other annular end of a surface, it very quickly, exponentially quickly, converges to a fixed end of a Delaunay surface. Delaunay surface also includes cylinder. Okay. Then we have, this is mostly about sort of small genus things. We have finite topology, genus-zero, zero surfaces. That means minimal surfaces. Remember, Green's minimal mean curvature. A finite total curvature, so you integrate the Gaussian curvature, you get something finite. The only examples you have are planes and catenoids. You have Schoen's result, which says the finite total curvature minimal surfaces with exactly two ends are catenoids. I mean, you have planes, but think of connected surfaces. You have parallel planes also, I guess. Then you have this beautiful result of Cullen, which says that, in fact, we don't have to use the word finite total curvature. In certain circumstances, finite topology, complete and embedded, means finite total curvature, which means we have these previous results. And in particular, the ends of finite total curvature surfaces are known to be asymptotic to planes and catenoids, again, the canonical examples. So this tells us the asymptotic behavior of what the surface looks like. It's got a finite number of ends, and they're going out into space and asymptotic to either planes, maybe have a bunch of planar ends and a bunch of catenoidal type ends. So this is about as good as you can get. You could start talking about moduli-based questions and so forth, but this is one of the great results that reduces essentially back to algebraic geometry. Because finite total curvature surfaces that are minimal, they have compactification, they're compact Riemann surfaces, and then the data, the analytic data that produces the surface is given by meromorphic data on that compact Riemann surface. Okay, so then we have pi1 equals 0 is just another shorthand way to say simply connected, because I'm trying to be very short here on this slide. Okay, so simply connected, zero surfaces are planes and helicoids. When they are proper, so we get this interesting word again, proper, right, means that in compact balls you see a compact part of area, finite amount of area in balls. Okay? And then we have this really beautiful result of Colli-Minkowski, which again makes everything kind of, you can say less and you get more, right? Or you can just say less. So complete zero surfaces, minimal surfaces, when you have finite topology, they're always proper. So you get that for free. So now you can say more things. Okay, so now you don't have to say maybe finite total curvature. You don't have to say proper. You can just talk about finite topology. Very nice. It simplifies the way we talk about the theorems in the subject. So this is kind of a very general classical slide that kind of summarizes the main sort of classical results. Okay, so we want to go away from that. Remember, we were trying to understand why are there no planes of a positive constant mean curvature in R3. So there are various approaches. One is via looking at surfaces of finite topology. Okay, finite topology just means compact Riemann surface minus a finite number of points up to homeomorphism. So that's what we're talking about when we say finite topology. So this is an important kind of result. It sounds a little strange, but it just says that these surfaces have positive injectivity radius. Okay. All right. So why is that important? Well, let's just take a look at this result. It says, suppose you have a complete, connected, embedded surface, H surface in R3. So we're looking at surfaces in R3. If that surface has positive injectivity radius, which we already know holds for finite topology surfaces. So, for example, finite topology surface, if it has positive injectivity radius, it is always properly embedded. Okay? And if the mean curvature is bigger than 0, not only is it properly embedded, but the norm of the second fundamental form is bounded. So it locally looks like a little graph. Small balls, it just looks like a little graph over its tangent space. So it has a nice picture, local picture. Okay. And where do some of the techniques come from here? One uses the uniqueness of the helicoid that I mentioned earlier for planes, non-flat planes are helicoids, and a lot of the techniques that Coley and Minicozzi used to prove their properness result for in the minimal setting. And I'm going to talk about some of those results in my talk, some generalizations of their work. So you'll see some of that more explicitly described in a minute. Okay, so what do we get? This is what I think is kind of really neat. This is like, it's a little hard to appreciate at this maybe, but okay, so I'm talking here about one disks. That means an embedded disk in R3 with constant mean curvature exactly 1. And you can make these be, you can think of, you can actually make stable examples, which are huge, They wind around, and you can put a disk into space. Very complicated, it can be stable. It can be a stable soap film, soap bubble. But what this is saying is that the intrinsic radius of such a disk, so if you think of the disk in the plane, round disk, you have the radius. That's the distance from the center to the boundary. So the radius is just the maximal distance from an interior point to the boundary. Intrinsic distance. So that's what we think of as radius. It matches up with the disk of radius r in the plane, right? It's got radius r. So there exists a constant r bigger than or equal to pi, such that if you look at any embedded one disk in R3, you are no point is further than this number from its boundary. I'm guessing probably the sharp number is pi itself. I mean, pi is, we certainly need at least pi. I'm guessing actually pi itself. I really don't know how to do that, because this is, it's a very theoretical result, and it's proof by contradiction kind of thing. Okay, so, but anyway, that's a very beautiful kind of basic result that this is very, very difficult to arrive at. So we're going to kind of see how do we get there. Of course, this immediately implies that there are no planes of positive constant mean curvature in R3, right? You just take a compact exhaustion of a plane by disks, then eventually one of those disks, the center point, is going to be arbitrarily far from its boundary. So you certainly cannot put planes in R3 of constant mean curvature. So we got that result we talked about before. And perhaps more interesting and more important, even though that's the first result about radius estimates is probably more interesting than this, we need curvature estimates in order to arrive at the radius estimates. Okay, so what does this say? It says, I'll just say it. You have a disk of constant mean curvature in R3, so a compact disk of radius. It's got a nice, say, maybe smooth boundary. If I'm intrinsically at least some distance, in this case, at least some distance epsilon, right? Point right. If I'm at least intrinsically some distance epsilon from its boundary, then I have a curvature estimate. Curvature can't be too big. Norm second fundamental form can't be too big. It's pretty flat looking. Okay, so that's a crucial estimate. Okay, so let me tell you about some of the results that go into proving those sort of basic results, curvature and radius estimates. So for people who are familiar with this, and I'm guessing less than half of the audience, there's Coley-Minicozzi developed a lot of techniques called Coley-Minicozzi theory, and one of the key techniques is something called the one-sided curvature estimate. Okay, so this, if you, of course, you can read it. It's kind of long and whatever. But let's look at the picture. What does the picture say? The surface, this blue curve, is supposed to represent a two-dimensional surface in R3. So we have this two-dimensional surface in R3. The center of that ball, let's think of as being the origin. Notice where the boundary is. The boundary of the surface does not intersect the disk, the horizontal disk of radius r in the xy plane. This horizontal line corresponds to the xy plane, okay? So we assume that the surface avoids that particular disk, and its boundary lies, well, I probably should. Let's think of its boundary lies outside of, actually, maybe not exactly right. Its boundary somehow, Anyway, think of its boundaries lying outside of the ball of radius r. I mean, in a sense, I could restrict to something. This is still a correct picture, but it's not the way I quite stated it. If the disk gets very close to the origin, then in fact it's graphical. So there's a universal estimate, epsilon, that doesn't depend on the mean curvature. So Coldi-Minicozzi had this result for h equal to 0. So we had to generalize this. One of the things that makes it harder is convex hull property is not true. So for example, when you intersect such a surface with the ball, you don't know you even have a disk anymore. Okay, so that presents some problems. So a bunch of different issues that come up because the surface is constant mean curvature. Okay, so this is, again, a nice generalization of one of Coldi-Minicozzi results for minimal disks. It says that, I'll try to paraphrase all the language up there. It says if you have an embedded constant mean curvature disk, maybe minimal, okay, and you take a point on it that's sufficiently far from the boundary. Okay, so in fact, the ball of radius r centered at that point is sufficiently far from the boundary. So you fix an r, there's a sort of universal constant c. Okay, I'm sorry, for any r. Okay, so if somehow, when you scale by this big constant c, you still don't hit the boundary of the disk, the intrinsic ball doesn't hit the boundary of that disk, then as you go away from the point, think of this point as being at the origin. As you go away from this point, there's a relationship between intrinsic and extrinsic distances as long as the norm of the second fundamental form is reasonably big somewhere in the ball. Now, if you have constant mean curvature, say 1, that's our given, right? Your norm of second fundamental form is already reasonably big. So let's think of not Coldi-Minicozzi's case, constant mean curvature not 0. We have we have an estimate on the norm of the second fundamental form just from the fact it doesn't have 0 constant mean curvature. So something we just get for free. So think of constant mean curvature 1, for example. You could say, as I travel away from the origin, I have to travel at a certain sort of speed, which is basically like my extrinsic distance from the origin. Okay, so that's a chord arc estimate. And again, immediately gives you simply connected constant mean curvature surfaces are proper. Immediately gives you that earlier result we talked about. Now I'm going to just go to real quickly remind people who know the subject, there's something called the Welerstrass representation. It's great. It's an analytic way to write down all minimal surfaces. So if you have a minimal surface in R3, you have its Gauss map to the 2-sphere. You stereographically project from the North Pole. Then that's a meromorphic function. You have the third coordinate function's harmonic. You can complexify its differential. You make a holomorphic differential. And you can recover the coordinates of the surface by path integration. So you pick a base point, and you look at path integrals. Okay? Then you can recover all surfaces of this way. And it's sort of, you can go back as long as there are no real periods on those holomorphic forms. Okay. So this is the way we create minimal surfaces. We take holomorphic data on a Riemann surface, we integrate it, and that's how we get mappings. So what this result is trying to tell us is that if you have an end of a finite topology minimal surface in R3, and let's suppose that end is embedded, that means it's an annulus with a compact boundary. What can we say about the asymptotic behavior of that end? How does it behave as it goes to infinity? Well, it's very restricted. Okay, so this picture, a picture tells 1,000 words, so let me just tell you. After rotating that annulus, okay, first of all, the annulus is going to be proper. That's one thing you have. And so it looks nice. It doesn't accumulate anywhere. So after some kind of rotation, there's a notion of horizontal to it. So you kind of see this as sort of horizontal in this picture. As I go up to plus infinity, I converge to a vertical helicoid. So if I translate down, I'll converge to a vertical helicoid. If I translate up, I'll get a vertical helicoid. So there are these sort of limiting helicoids. And a helicoid, which is horizontal, has a notion of an axis, has a vertical axis. Those produce lines. So you see a line RT for the top helicoid, a line RB for the bottom helicoid. And then we have the rest of the surface. So outside of a big cylinder, this is what we see. We see a multigraph which has a certain, it's very flat. It has a b over 2 pi log r sort of growth. It's a multigraph. That growth, of course, goes to 0 as you go up to infinity. But anyway, that's the behavior of the sort of the sides. And notice we have two constants. We have that b constant in the logarithmic growth, and we also have this separation distance between the axes of the two straight lines. So that just comes from with a flux. So you do a flux, you rotate the surface so the flux has that form, then you get that explicit picture. So what that means is there is an example that's embedded that looks like that, and your example is asymptotic to it. So it very quickly converges to that standard picture. So this is about the best you could say about properties of surfaces. If, for example, if the A is 0 and the B are 0, then you're going to get you get that you're asymptotic to a helicoid. That's what you end up having. Okay, so another thing we get out of the Welerstrass representation is, let me just follow my time. I guess I remember approximately when I started. Okay, so this is one of the really beautiful questions. So we're getting to questions which I think, hopefully I'll be involved in solving it, but like really hard to believe problems. You say, well, I just proved such and such a theorem. And you say, well, that's not true. And those are the best theorems, right? Nobody believes that's true. And then you prove it. So this, one consequence of the Welerstrass representation is that we can prove something. That's what this theorem says. It says you take any smooth, compact, bounded domain in R3, you take any open Riemann, open surface, then I can properly, minimally immerse that surface into that particular domain. So if it was a ball, and in the subball, I see a finite amount of area, and the surface somehow just limits to the boundary sphere. It could limit to the entire sphere, but let's not worry about that. We just have this very nice result for any smooth bounded domain. It's a proper immersion. And what actually is the case, oh, even better, each individual end of this immersion, if you take two different ends, so that means something topological, okay? If you take two different ends, this immersion has the property that those ends have limit sets, which are compact on the boundary of that domain, and those compact sets are disjoint. So they have this very important control, because we want to prove something that's impossible. A lot of people say, that's not true, it's impossible. So that control gives us a lot and leads us to this particular picture. So this is, this domain, this D infinity domain, is a particular domain. It's just not, it's not any smooth, sort of almost smooth domain. It's a picture, it's a domain which actually looks like the way it's drawn. And on it, it has lots of compact surfaces. It has Mobius strips. It has annuli, minimal annuli. It has minimal annuli with handles. And somehow we'd like to connect them all up and, like a bridge theorem somehow, and make the surface complete and embedded. And the claim is that we can do that. We don't know if we can do that, but the claim is we can do that under certain restrictions. So the theorem set, the conjecture is that, take your favorite open surface. What's a necessary and sufficient topological condition on that surface so that it will admit a complete, proper minimal embedding into this domain? And the condition is very simple. Every end has infinite genus. Okay? That's the necessary and sufficient condition. There's some related conjecture. If you don't worry about this particular domain, you can say, what's a necessary and sufficient condition for an open surface to admit a bounded, complete embedding into R3? Bounded, so it lies on a ball, complete and embedded. It's the same condition. Every end must have infinite genus. So it sort of the right conjecture here sort of solves two big problems at the same time. Not only that's a necessary condition to exist complete and embedded and bounded, But it's also, you can actually do it in a proper way. And if you have a finite number of non-orientable ends on your surface, then in fact you can do this in a smooth domain. Or if it's orientable, you can always do it in a round ball. You can in fact do it in a round ball. So that control from the previous theorem hopefully will lead to solution of that. Okay, so let me just kind of go through here quickly. This is our summary of things that we used to know, or we've known at least for some time. So complete embedded minimal surface in R3 is proper if it has finite topology. Harold Rosenberg and I generalized that a little bit using basically their techniques. We also generalize it in a manifold setting somehow. Okay, so now we get a harder one. This result with Meeks, Pérez, and Ros is when you go from finite topology to infinite topology, well, think of finite genus to finite genus with infinite topology. So finite topology has finite genus and a finite number of ends. But you could also say finite genus and an infinite number of ends. And if you only have a countable number of ends, then we can generalize what Colding and Nicosi did. Much harder to do, but we can do that. And also, we know that properly embedded finite genus minimal surfaces have bounded second fundamental form, or bounded curvature. So here's one of the important conjectures. I always feel like we're almost there, we never get there. I think Giuseppe Tenaglia and I can prove this when the mean curvature is positive. So this is, again, one of these very hard, very sort of easy to state questions, but it's very hard. So I take a complete embedded H surface in R3 with finite genus. Okay? Then I would say it's always properly embedded. It's complete and embedded, it's properly embedded. So if H is positive, I'm pretty sure that we can actually do that. In fact, we can actually prove estimates about the area growth. We can prove it has to have at most cubical area growth. So in particular, you can't have an infinite amount of area in a given region. And that implies properness. Okay. Okay, so let me tell you about a little bit more about some of these really beautiful results. Here's an example of genus-zero, minimal, and with an infinite number of ends. So this is a surface in R3. So these examples were classified by Riemann. They're foliated by round circles, straight lines, and parallel planes. The ends of the surface is asymptotic to sort of an infinite stack of parallel planes. So as I go out sideways, I actually converge to planes. And so this is but infinite genus genus-zero, infinite number of ends. And it turns out we can actually do a complete classification of genus-zero, infinite number of ends. Those are Riemann's examples. So in fact, we can do genus-zero. So what are all the genus-zero properly embedded minimal surfaces in R3 of genus-zero? You have the Riemann example, and you have limits of the Riemann example. And the limits produce catenoids. It's a family of examples. And another limit is helicoid. So the moduli space is exactly a curve. And somehow the endpoints are, something happens at the endpoints, which gives you helicoids and catenoids. Okay, let me just think about this. Okay, so I'm just wondering what I should do here. Okay, well, we have, there's also this sort of general thing. What are the topological types for minimal surfaces of finite topology? And so one of the simple questions, conjecture, I guess, by a number of people, Harold Rosenberg and I, for example, that if you have one end, so you take a compact surface, remove one point, does that admit a complete or proper embedding, proper minimal embedding into R3? One-ended surfaces. And the answer is, for any surface, you can do this. Another part of the conjecture that Harold and I had was that you can do it in only one way. So if you take a torus and you remove a point from it, yes, you can do it by this theorem. There's a proper minimal embedding in R3. But there's only one, up to an isometry of R3 and a homothety. So there's really only one way to do it. We still don't know that uniqueness part. Another sort of thing is that we have, when you're looking at finite genus surfaces, we know how they behave asymptotically. So just probably ignore all this reading. We have sort of, our classical examples are canonical sort of representatives of how the general examples behave. All right, so let's not worry about reading it. Now we come to a very interesting philosophical sort of result. Maybe let's look at the second bullet here. It says that if you look at a complete embedded minimal surface in R3 of finite index, so if you look at the index form, it's got a finite number of negative eigenvalues. I mean, that's one way to think of it. Okay, these finite index examples you can compactify, so things really do make sense. Okay, so you have finite, you fix the genus, then the claim is the index of a surface with finite index is limited by some particular number. So when you do sort of higher order minimax problems, say in some 3-manifold, you rescale. If you bound the genus of the surfaces through which you do the minimax, it says the index of an associated singularity, which we get by rescaling, it can't go to infinity. It's kind of slightly related to the first talk today, okay? Some sense. I mean, it's related to that. And I won't say anything about the first bullet. Okay. Another thing that comes out of this whole general theory are pictures. Pictures that tell how things behave when things go wrong. So things go wrong, like curvature blows up or something, but still a lot of things go good. There's a lot of regularity in how things get bad, right? Bad happens, and you have to live with it. So if you look at this one-parameter family of Riemann examples, these are foliated, remember, by round circles and straight lines and, say, horizontal planes, but there's a family of them, right? There's a family of these examples. And you can take a parameter in this one-parameter family, you can take a parameter going to infinity and scale it appropriately. What these examples converge to are foliations of R3, say, by horizontal planes. But you don't converge smoothly to the foliation. You don't converge smoothly along two lines, say, two vertical lines. That's the behavior. Joaquin Pérez and I and Antonio Ross, we studied this back in around 1990, I don't know, 97 or something like that. We studied these kinds of structures, and from the structures, we could prove uniqueness theorems, like this, almost related to that uniqueness theorem that we talked about genus-zero surfaces with an infinite number of ends. There were more hypotheses, but these structures are very, very important. And we call these structures sort of limiting behavior minimal parking garage structures. So there's somehow a singular limit that has a lot of structure of a foliation and curves along which the second fundamental form blows up. Okay. Another important invariant in constant mean curvature theory, minimal surface theory, are fluxes. Okay. So if you just look at the second dot there, we have a closed curve gamma on the surface. We're looking at a surface of constant mean curvature, capital H. Then we get a homological invariant. If you look at that integral, okay, so gamma is the curve, C is the unit normal to M along thing, you can get a number. So associated to any closed curve, you get somehow a homological invariant. This is a homological number, defined number. In the special case, the surface is an annulus. There's only one generator for the first homology group, and we just call that number the flux of the annulus. So when you have an annulus, there's not much going on in the first homology group, so there's just a number that's associated to the surface. Okay. It might be 0, right? It could be the number could be 0. In fact, it's 0 sometimes. So just keep in mind, it's not necessarily a non-zero number. Okay. Okay, again, this is, I'm sorry, don't try to read this. This theorem is a generalization of a previous result of Coulomb-Nicosi, and it tells you what are the limits of compact surfaces of constant mean curvature. Maybe the constant mean curvature changes during the sequence. And I want the boundaries of these surfaces to go to infinity. Okay, so I have a sequence of compact constant mean curvature of surfaces, boundaries are going to infinity. What do I get for limits? And interesting enough, you actually get nice limits. The limits could be singular in the sense they might converge to a minimal parking garage structure. So they might converge to foliation of R3 by horizontal planes, non-smooth convergence, and so forth. But anyway, this theorem basically describes what are those limits. You have to read it a little more carefully. But it's nice. You get an answer. Always a subsequence converges to some nice kind of limit object. Okay, I don't think I'm going to do this proof, but it's there. It somehow uses that previous theorem. So remember, we said there were curvature estimates for constant mean curvature disks, or one disks. They're curvature estimates. As you go away from the boundary, you have a curvature estimate. We like to say the same thing happens if we make instead of a disk, we use an annulus. Okay? Now, annulus has a flux, has a number associated to it. That number is either 0 or it's not 0. Okay? So there's sort of like two theorems here. If it's 0, that's one result. Or let's just take the case where it's not 0. So once you have that number, the flux is at least that number, then there again is a universal curvature estimate. So as I go away from the boundary, I have a uniform estimate on the norm of the second fundamental form. So in particular, ends of finite topology, constant mean curvature surfaces, they're annuli. They have a number associated to them. So they have bounded second fundamental form. Okay, so if you just think about that for a minute. So, and definitely, it's a blow-up argument, and you do different things with the previous things. You use the flux somehow in a crucial way. So, again, I don't think that will be useful to do this. I see my talk is way too long, way too long for 1 hour, I guess. Okay, so yeah, I guess I'm about 3/4 through. So maybe I'll go a little slower now, since I don't have to prove that. Okay, so we have these beautiful classical examples of minimal surfaces, right? Triply periodic minimal surfaces of the 18th century, right, or 19th century. So we had Riemann, Schwartz, and just a whole bunch of Schurk, a whole bunch of people found examples of minimal surfaces. In particular, triply periodic. Most of them were triply periodic, not all of them, but most of them were. So we can really think of these triply periodic minimal surfaces as being compact minimal surfaces in a flat 3 torus, right? We divide up by the translations. Okay, and these surfaces actually also come in nature. I used to have a great slide of sea urchin shells, and you could see these surfaces of constant mean curvature, actually positive mean curvature for sea urchin shells, and they look very similar to these sort of pictures. You also have Fermi surfaces, equipotential surfaces in crystals, like a salt crystal. You have interfaces between materials and polymer science. Anyway, you see these as boundary surfaces. They're trying to minimize the energy. They come close to minimizing area with respect to volume, preserving deformations. Okay, so the question is, if you fix the 3 torus, you fix the genus of the surface, and you fix the mean curvature, or a range for the mean curvature, can you get area estimates? We can't get curvature estimates, but can you get area estimates? And can you understand what happens when you take a sequence? Is there somehow still a compactification of moduli space? Maybe the curvature blows up, but it does in a very standard, particular way, kind of like anyway, in the previous talk. Okay, so for minimal, it turns out for minimal surfaces, you can take, for example, genus 3 surfaces. There's no area estimate. So this is really a result about positive mean curvature. So we have this result. If you take a 3 torus, for example, and you fix the genus and you fix the mean curvature away from 0, kind of fix it, then we have area estimates for these surfaces. And in fact, we actually get a compactification of the moduli space. So somehow we have a nice structure when the curvature doesn't. We have area estimates. To get compactness, we need curvature estimates. Well, those don't always work, but they fail in a very particular way. But the moduli space is compact. If the moduli space is compact, it's not hard to see that one has to has a estimate on the index of all these surfaces. And these problems come up from minimax questions and stuff like that. Okay, so anyway, so in fact, the area can only grow linearly with the genus, and the index can also only grow linearly. And in fact, you can prove similar kinds of results for like the three-sphere or for negative curvature, hyperbolic three-manifolds, compact hyperbolic three-manifolds. In that case, you can even let h be equal to 0. Okay, so, and the other, yeah, flat is bad for h equal to 0. The other cases, h equal to 0 is not so important, not being 0. Okay, so let me tell you a little bit about this story. This is actually a very beautiful story and kind of again gets into Simon Donaldson's talk, how you understand some of these problems by sort of pointed Hausdorff, Gromov-Hausdorff compactness of certain spaces. Okay, so maybe I should back. Oh, let me go back here. Try to go back. There we go. Okay, there we are. Okay, let me just put the first theorem. This theorem is talking about foliations of a manifold by surfaces of constant mean curvature. Okay, okay, you can prove some regularity about such things in 3 dimensions, but let's suppose we're just thinking smooth, just to make it easier. The result is more general, but okay, so CMC, well, for CMC to really make sense, I need a transversely, or I need to have transversely oriented surfaces. So I need to know what the normal, sort of a normal field is, or I need to do something called transversely oriented. So I assume the foliation is transversely oriented, so then it makes sense to talk about the mean curvature as a function. We don't have to worry about absolute values or something like that. So this says if you have a foliation of a closed orientable three-manifold, and you have some isolated set, finite set of points where it doesn't extend across those points, then you must be the three-sphere. And for the three-sphere, there are lots of examples like this. So even the round metric three-sphere, there are lots of these constant mean curvature foliations with isolated singularities, or two singularities. You can make actually a little bit more. Anyway. Okay, so that's one thing. So if you have singularities, you're very restricted on what the manifold is. This is also a very pretty result that uses some of these compactness, sort of pointed Hausdorff, Gromov-Hausdorff compactness sort of approaches. So it says that if you have a CMC foliation, you can actually use, if you know what lamination is, you could even say lamination, a CMC lamination of a punctured Riemannian ball. So think it's a local question. I'm in a three-manifold. I've isolated some singularity, possible singularity, and I look at a little ball around that point. Can I extend the lamination or foliation across that point? And the answer is right. So if and only if, well, okay, if it's a CMC foliation, if and only if the mean curvature function is bounded in some neighborhood of P. Right, so this is actually, you get an extension, right, you get an extension called a weak CMC foliation. So in other words, everything's graphical in the neighborhood of that point. Graphical of the tangents. There's a leaf that goes through the singular point, and everything's graphical and nice around that point. So here's a picture of what kind of happens in R3. You say, well, how do you have singularities? Just think of round spheres having infinite radius, get a family of planes, then the radius goes down again. So here's a nice picture. I have an example with 2 points, a foliation of R3 with 2 singular points. And in fact, any CMC foliation of R3 in the complement of a countable closed set, in fact, each of the leaves is part of a round sphere or a flat plane. So, a nice structure theorem. And again, we have these sort of, it's related to the previous slide, removable singularity properties of these laminations. And a nice question, kind of going back to the first talk today. We'd like to, for example, prove theorem, that's the last theorem about removable singularities. We'd like to prove that if the singular set of the lamination was codimension, and we're saying R3, it's a local question. If that has small Hausdorff dimension, if the Hausdorff dimension was less than 1, in fact, you should be able to extend across, say, if the mean curvature doesn't blow up, we should be able to extend across that CMC lamination or foliation. Anyway, so now let's going to shift gears a little bit. What about foliations of a compact 3-manifold with all the leaves being constant mean curvature? Take your favorite 3-manifold. Can I find a Riemannian metric and a foliation so that all the leaves have constant mean curvature? And that's what this question is about. I'm going to be kind of brief on it. All right, so that's the question. Now, but I won't say anything about it. Sullivan had some results about minimal case. So the answer, I'll just mostly on these slides tell you the answer. There's a picture and so forth on the next slide that's an outline of what the proof is. But I'm just going to focus, what is this result? So if you take a compact 3-manifold, smooth compact 3-manifold, you ask this question, when does it emit a smooth CMC foliation for some Riemannian metric? And the condition is completely topological, if and only if its order characteristic is 0, which is if and only if it emits a transversely oriented foliation by going back to Thurston. So the question is, can you somehow take Thurston's foliation, modify it appropriately so that all the leaves, and find a metric so that all the leaves have constant mean curvature. And that's basically the strategy of the proof. And in the case of 3-manifolds, no problem. Odd dimensions, order characteristic is always 0. So there are some little bit delicate aspects of this when the manifold is non-orientable. So you have to do some slight generalizations like of Sullivan's theorem and so forth. But basically, it's a doable problem. Another interesting property of CMC foliations, this CMC foliation can actually be taken so that it's not minimal. So you could say CMC foliation, not minimal. So there's a range of values for the mean curvature. And then once you have that range of values, it turns out that for every value of the mean curvature, there exists a compact leaf. So once you say you go away from minimal, you're forced to have lots of compact leaves, at least one for every value of the mean curvature. So I always kind of hope that this could be useful in trying to study questions in topology, 3-manifolds. You have something to work with. You can do something, maybe. And this is just kind of a sketch of the proof. And hopefully, and we have notes and everything like that. So the idea is to construct some things that look like what are called Reeb components of constant mean curvature. You take a foliation that Sullivan gives you. You do something called trivialization. You sew these things in. You sew them in such a way you can apply Sullivan's condition that allows somehow to make a minimal foliation. Anyway, and then you do something with Moser's theorem to modify metrics and so forth. Again, don't be focused on the proof. Okay, so now I'm getting to the last part of my talk. I think I have about 5 minutes. Okay, so invariance. So if you have a 3-manifold, not necessarily compact, you can define an invariant. Say maybe people are more familiar with that last invariant, the Cheeger constant. It comes up from when you solve like isoperimetric problems. You don't always have solutions of these problems for non-compact manifolds, but sometimes, like in a homogeneous setting, you can prove you have these solutions. Anyway, you have the Cheeger constant. So you look at trying to solve like the isoperimetric problem for domains of varying volume. So you take the area of the boundary of those domains, and you divide by the volume, and you try to take the infimum as over all such compact domains. That's called the Cheeger constant. But you have a closely related thing. So when you actually can solve the isoperimetric problem, you get a boundary surface of constant mean curvature. Okay? That produces a number in that top line. So h of y of this 3-manifold, I'm going to focus on 3 manifolds, it's defined in general, but 3 manifold, I take the infimum of the maximums of the mean curvatures functions of all compact immersed surfaces in the manifold. So it's kind of hard to imagine exactly what that really means. But just think of the case of constant mean curvature. I don't want to look at all immersed surfaces. Say you just look at constant mean curvature surface. Then I have its mean curvature. I take the absolute value of those numbers, and then I take the infimum. It's kind of easier to understand, but we actually have this more general definition. That's called the critical mean curvature of the space. And important for what I'm going to talk about next is this, this equation that relates these two numbers, okay? Because lots of times you have one of the numbers you can calculate very easily. For example, the Cheeger constants of certain spaces, very easy to calculate in certain cases. And you have this number you don't know too much about. It's a little strange. And it tells you that those two numbers are the same in certain cases. So if Y is simply connected, homogeneous three-manifold, then there's this relationship between the numbers. And part of the proof, for example, shows that if you're in such a manifold and you take a big volume, so we're looking at a non-compact homogeneous three-manifold, take a big volume, solve the isoparametric problem, look at the mean curvature of its boundary. It's actually, as the volume gets bigger and bigger, it's actually, you can prove it converges to 2 times the critical mean curvature. So there's lots of interesting things along the way, but just these numbers being the same is very useful for other problems. So, yeah, okay. Well, I actually have some, I can sort of briefly tell you something here. So what are the simply connected homogeneous three-manifolds? Well, you have products of spheres, round spheres with the real number line. And you have what are called metric Lie groups. Lie group, three-dimensional Lie group with left invariant metric. So I'm just going to call those metric Lie groups. Okay. In the special case of a round sphere across R, Abrich and Rosenberg proved a very beautiful result that says that all the constant mean curvature spheres in these spaces are spheres of revolution. And you can write them down explicitly. You can write down an ordinary differential equation, produce them. You find that there's one for every possible mean curvature. So you take a number bigger than or equal to 0, there's in fact, an embedded two-sphere with that mean curvature, and they come in a parameters, unique one for each mean curvature. All right, so here is, and of course, that generalizes somehow Hoff's theorem. So think of this as a generalization of Hoff's theorem. So Hoff's theorem says an immersed sphere in R3 of constant mean curvature is round. Okay, of course. And then, of course, you can see there's a unique sphere for each mean curvature because the mean curvature is 1 over the radius. So you can actually understand the moduli space for all examples. So this is a related theorem. We'd really like to generalize Hoff's theorem. People have been chipping away at this problem, not really getting too far before. So we use very strongly the Lie group structure. So we don't have to deal with S2 cross R, right? S2 cross R is solved by Abrich and Rosenberg. So we're looking at all those other examples. SU2 with a left invariant metric. We're looking at R3 with a left invariant metric, with, of course, some group structure in the background. So we're looking at somehow a 3-parameter family of different spaces. So what happens? So if you are topologically R3, then you have this 1-parameter family of examples, and they're parametrized, their mean curvatures are parametrized by an open interval between this sort of critical mean curvature number, which can be calculated in terms of the Cheeger constant, up to infinity, okay? So that's the range of the mean curvatures, and there's 1 for each value of the mean curvature. In fact, they come in a nice analytic family, these spheres. If you're S3, that means your group structure is SU2, then again, it's a very, very pretty family. You get there you get a unique sphere for every possible value of the mean curvature. Notice in the first case, if h of x is any value at all, you don't get, right? H of x, remember, is always bigger than or equal to 0. So in the first case, R3 case, you don't get certain things. In the other case, you get you sort of somehow get 1 sphere for each possible mean curvature. Okay, and in fact, you have a bound on the areas of all those constant mean curvature spheres. And because they come in a family, it's not too hard to prove by the maximum principle that they're all Alexandrov embedded. They all bound immersed balls. On their mean convex side, there's an immersed ball. Okay, so real fast, there's 2 slides. It tells you how to do this. Okay, this is again one of these works in progress. I think it's going to be at least a year till we haven't had the SU2 case. We had that online, but this is a non-trivial result. There's some parts of it that certainly at least probably 100 pages long. So, okay, so but the steps are really neat. The first step is that we only focus on index 1 spheres. So all these spheres that you produce have index 1 and nullity 3. That means you have a 3-dimensional family of Jacobi fields that come from, so you're a homogeneous manifold, so you're going to have 3 from the killing fields. Okay, so that's just Chang's theorem. The stability operator is a Schrodinger operator. You're in the 2-sphere, and you can, if you have index 1 for that operator, then the nullity can be at most 3. Okay. And we have at least 3 because we're in a homogeneous 3 manifold. We can move in 3 different directions. Okay, step 1. So we're focusing, keep in mind, is index 1. Implicit function theorem immediately gives you that the space of all examples really come in 1-parameter families. If you have an example of index 1, you can move it a little bit through mean curvature changes as you move it. That's pretty standard. Left invariant Gauss map. So at each point, you can take the unit normal, translate it to the origin by left translation. You have a map to the 2-sphere. Then that's a diffeomorphism of degree 1 with respect to the outward pointing normal on the 2-sphere. That's an interesting argument. I'm not going to talk about that either. That immediately gives curvature estimates. As long as you don't let the mean curvature go to plus infinity. As long as you bound from above the mean curvature in absolute value, you have curvature estimates by rescaling. Step 4 is the really hard, that's the hard part. So if you're in SU2, you prove that these index 1 spheres have a bound on their area. There's an upper bound. They can't have too much area. If you're not SU2, that means you're R3 topologically, then what you do is you prove area estimates once you stay away from the critical mean curvature. So if you go to the critical mean curvature and just add a little something to it, then you get area estimates. So that's really, really subtle. And that uses a lot of this sort of Gromov-Hausdorff manifolds with boundary compactness, sort of abstract compactness results. I mean, a lot of other results. I mean, it's not just that, but that's, and it's not hard to see there are no h of x spheres in this case. And the rest of the argument's pretty straightforward, so I'll just say it real fast. So then you have this moduli space. Remember, they're curves. Well, these curves, by the area and curvature estimates, you end up going all the way up to plus infinity. So this family goes to really, really big mean curvature. When it's really big mean curvature, it's almost a little round sphere by rescaling arguments. And there's a unique almost a little round sphere. Those are stable. So when the mean curvature is really big, it's easy to say there's only one. So you just take where you are and just go out to here. So you find out there's only one curve in the moduli space. So that's basically what you get from the previous estimates. Novel kind of argument here is like what Hoff does. We want to create a holomorphic differential, except we can't do that. We can create a complex differential by using the fact that Gauss map is a diffeomorphism and comparing a given other example with the same mean curvature as sigma with sigma itself. You can do left translation. You can try to compare the second fundamental forms at the corresponding place where the Gauss map is a same normal vectors. And from that, some work, you can create a complex differential with isolated zeros. And now we're really back to sort of Hoff space. Once you do that, you're really home free. You can prove that there are no other constant mean curvature surfaces with that mean curvature that are different than sigma. Sigma is the only one. So that's you're kind of in elementary topology or something. So in the end, you get the whole result. So I think I think I'll probably just stop right there.